Recall that, well, it's not exactly from Honors Linear Algebra 1, not exactly, but from part 3 of this course, which is that when an operator with respect to some basis is upper triangular, then the elements in the diagonal, they are the eigenvalues of the operator, but not only that, the number of times each eigenvalue, each number appears in the diagonal is exactly the algebraic multiplicity of this eigenvalue. We didn't state this as a theorem, but we have been using it. We even used it in some exercises, and you can see that by looking what the matrix of T minus lambda I, this matrix, if you raise it to the power n, you will see what will be the dimension of the kernel of this operator. If you look at the dimension of the kernel of this operator, it will be exactly how many times this number lambda appears in the diagonal. Now, in the fourth part of this course, we saw what it means to complexify a vector space, which now I'm writing in quotation marks, but maybe these quotation marks are a little too late. Basically, a vector from this space, we always can express this as a real vector plus I times an imaginary vector, as long as we know what that means. And then we can also complexify an operator by applying it to the real and imaginary part of each complex vector separately. And the characteristic polynomial of an operator was defined in part 3 of this course as the product over all eigenvalues of z minus the eigenvalues listed with multiplicity, in case our field is the field of complex numbers. And in case our field is the field of real numbers, it was in the part 4 of this course, then we defined that the characteristic polynomial of an operator on a real vector space was simply given by the characteristic polynomial of the complexification of that operator. And then we proved that in that case the coefficients of the polynomial, once we expand, because it's written here in form of a product, once we expand it, these coefficients will be all real. Finally, this one is from the first half of this 2-semester course. This was in Honors Linear Algebra 1. It says when the field is the field of complex numbers, every operator T, for every operator T and a linear operator on a finite dimensional complex vector space, there exists a basis B for that space such that the operator T written with respect to that basis is upper triangular. It is upper triangular. And so in case the field is the field of reals, we're going to observe the following. If the field is the field of reals, then we can complexify the operator, and in that case still find a basis for which it is upper triangular. That basis does not need to be made by real vectors. Maybe the elements in that basis will necessarily have non-zero real and imaginary part, but still we're going to use this result from Honors Linear Algebra 1. We're going to need it.